Hi everyone, welcome to Go Classes. How are you all? So this is our part 3 of pumping lemma. We have already seen what is pumping lemma. We have taken many questions, many examples, and I hope you are expert of pumping lemma right now. In this session, we are going to study the proof of pumping lemma. Okay, please tell me part 1, part 2, pumping lemma part 1, part 2. Did you understand? And are you feeling confidence in pumping lemma? Please tell me. This pumping lemma, this is quite easy and analytical. Let me tell you, whenever you are solving any question of pumping lemma, you will not feel bored. Yes or no? You will never feel bored because this is analytical topic. You need to use your brain. Okay, 100% use of your brain. You know, there is a quote, 100% use of your brain. So that's the point. This pumping lemma, this is quite interesting topic. Now let's see the proof of this pumping lemma. So in this lecture, what we are going to study, we will see the proof of pumping lemma for regular languages, and we will also see some type of questions that are possible in pumping lemma, how to solve them with many examples. This is our purpose for this part 3. Okay, so before we see this proof, let's start with this question that I gave you in the last session. This question I gave you as a homework. Did you try this question? In the part 2, this question I gave you as a homework. So let's see this question. Prove that the language is not regular. So this question, the language is given to you. W has equal number of ones, 0 and ones. Prove that this language is not regular. Now, we are using the pumping lemma to prove L is non-regular. Suppose length P is given to you. Which of the following W we can choose for our proof? Okay, so remember, what is our purpose? Tell me what is our purpose. We want to prove, using pumping lemma, we want to prove that L is regular. Okay, using pumping lemma, we want to prove L is regular. So tell me how can you prove L is L is non-regular using pumping lemma? How can you prove that L is non-regular? Your language is given to you. Now using pumping lemma, how can you prove that L is non-regular? You can say that for this L, whatever P you take, for this L, whatever magical number P you take, yes or no? Whatever P you take, there is a string which violates. There is a violating string. There is a string which says that I will not pump. There is a violating candidate string. Agree? Do you agree? This is what we do. Candidate string. So very simple. I can say for this language L, whatever P you take. Okay, so some arbitrary P, arbitrary, or I can say abstract P you take. This P can be anything. So arbitrary P you take, and for this P, there is a violating candidate string. Okay, a string which violates. Violating candidate string. What that means? That means a string which will not pump. A string which does not pump. A string which does not pump. Which does not pump. Correct? Okay. So a candidate string which does not pump. Now you tell me, which of these strings, if your pumping length is already given to you, let's assume this is the pumping length we are taking. We are assuming this pumping length. So if we take this pumping length, then tell me which string will help you to prove that this language is non-regular. There exists, remember, there is some violating string. We only care about there is a violating string. There is some violating string. We only need at least one violating string. At least one violating string we need. Yes or no? Agree or not? We need at least one violating string. Some violating string we need. So you tell me. Let's start with this. 0 power P by 2, 1 power P by 2. Will it violate? Will it not pump? This string, will it not pump? So for example, first of all, you tell me, is this candidate string? Is this candidate string? Tell me, is this candidate string? Let me know. Is this candidate string? See, already this P is already given to you. Okay. Now, for this P, first of all, tell me what will be the candidate string? What will be the candidate strings? What are the candidate strings? Which strings have the authority to violate or satisfy? Those strings which belong to L and whose length is greater than equal to P. Whose length is greater than equal to P. Okay, this type of strings, these are the candidate string. Now you can notice if P is odd, then this is not a candidate string. Yes or no? You can easily notice if P is odd. If P is odd, you can easily notice that if P is odd, I don't know what is P. Agree or not? I cannot put any restriction on P. Do you agree with me? I cannot say that P is even. I cannot say that. I cannot say that. I cannot put any restriction on P. So if P is odd, if P is odd, then I can say this string is not candidate string. Let's call it option A. Then A is not candidate string. A is not candidate string. Okay, so this is the point. A is not candidate string. Anyway, even if you assume that P is even, okay, let's assume even if you assume P is even, then is it candidate string? Let's assume for a moment. Okay, for a moment, assume P is even. Assume P is even. Now you tell me, will this pump or not? If assume P is even, for example, maybe P is, let's assume P is 20. Okay, now in this situation, this string in option A, this is your option A. Okay, this string means 0 power 10, 1 power 10. You tell me one thing, this string, now this is a candidate string, yes or no? This belongs to L, and also its length is greater than equal to 20. You can notice this length, this string belongs to L, and also you can notice the length of this string that is greater than or equal to 20. Now you tell me, will it pump or not? This string, will it pump or not? I am asking you a simple question. This string, will it pump? Will it pump or will it violate? Will it pump or will it violate? So let's check. Will it pump? So this is your string 0, 0, 0, 0, and then 1, 1, 1, 1. Now you tell me, in which area you will find Y? In which area are you going to find Y? Your P is equal to 20. This is your P. So in this area, you will find Y. In this entire area, within first P symbols. These are the within first P symbols. So within first P symbols, you are going to find Y. Okay, so let's find Y. So tell me which Y will work? Which Y will work? You can notice this Y will work. If I take this Y will definitely work. This Y works. You can repeat it any number of times. The resulting string will belong to L. Yes or no? You can repeat this any number of times. You can repeat this. Okay, so this is 0, 0, 0, 0, and then 1, 1, 1, 1. Now I am saying that this Y will work. This Y will work. Then in this situation, what is your X? This is your X. This is your X, and this is your Y. This is your Z. Now you can easily notice, if I repeat it any number of times, number of 0 equal to number of 1. Agree or not? If I repeat it any number of times, if I do X, Y power n, Z, where n is greater than equal to 0, I repeat it any number of times, the resulting string will have number of 0 equal to number of 1. In the resulting string, number of 0 will be equal to number of 1. So I can say this will belong to L. This resulting string will belong to L. Yes or no? Tell me one thing. This string, does it belong to L? 0, 0, 0, 1, 0, 1, 0, 1, 1, 1. Will it belong to L? Yes, of course it belongs to L. The language is number of 0 equal to number of 1. Number of 0 equal to number of 1. Remember, your language is number of 0 equal to number of 1. This is your language. That number of 0 is equal to number of 1. This is your language. In your language, you have this type of strings. For example, this string is also there. 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 Is this point clear? Let me know. Okay, this string is also there. This string is also there. This string is also there. I hope all these points are clear. This string is also there. So remember, this is your language. I hope this point is clear. So this is the language. So here you can notice, if you repeat this Y any number of times, the resulting string, this is your resulting string, that will have equal number of 0, 1. So the resulting string will belong to L. So I can say this string is pumping. Will this string pump? And the answer is yes, this string is pumping. Correct? Yes or no, can I say? So I can say, will this string pump? The answer is yes. So if this is pumping, if this string is pumping, will it help you prove non-regularity? If this string is pumping, then will it help you to prove non-regularity? The question is asking which will help you to prove non-regularity. The question is asking which string will help you to prove non-regularity. So this string is pumping. So this is useless for us. This is useless to prove non-regularity. To prove n L equal to non-regular. To prove L is a non-regular. I hope this point is clear. So remember, this is useless to prove non-regular because this is pumping. This string is pumping. So this string is useless. So this string is not the answer. Okay, so whatever you do, if you assume p equal to even, then also this string is not the answer. If you assume p equal to odd, then this is not even a candidate string. So whatever you do, this string is not your desired string. This is not your desired string. So this string is not the answer. Now tell me about the next. Is this string the answer? The second string, will it pump or not? Yes, this is a candidate string. This is definitely a candidate string. Okay, because you can notice this string, let's call it option B. This string, option B, length is greater than equal to P. And you can notice this belongs to L. So this is a candidate string. Will it pump or not? Will it pump? Simple question. Will it pump? Will it pump? Let's check. So for this string, this is your string 0, 1, 0, 1, 0, 1, and so on 0, 1. Okay, this is your string. Now you tell me in which area you will find the y. In which area you will find y? In which area? In the first p symbols. Yes or no? Somewhere you have some p symbols. Okay, this entire string has 2p symbols. This entire string has 2p symbols, but somewhere you have the p symbols somewhere. Now you tell me, will it pump? Will it pump this string? So these are the, let's assume these are the first p symbols. These are the first p symbols. So will it pump? Yes, this will pump. You can take this as y. You can take this as y. Correct? You can take this as y. You can take this as y. Now you can easily notice this y will work. You can repeat this y any number of times. You can repeat it any number of times. You can easily notice that x, y power n, z, that will belong to L for all n greater than equal to 0. Okay, so very simple. So this is the idea. So I can say this string will also pump. Will it pump? The answer is yes. If it is pumping, will it help you to prove L is non-regular? Will it help you? So if this is pumping, so I can say this is useless. So this string is useless. So this string, option B, this 0, 1 power p is useless to prove non-regularity because this is pumping. Okay, so very simple. Now you tell me the next one. So remember, this is also not the answer. This is also not your answer. What about the next one? Tell me about this one. 0 power p, 1 power p. What about this? What about this? Will it pump? First of all, is this candidate string? Yes. Yes, this is a candidate string. This string matters to us. Yes, this is a candidate string because this string 0 power p, 1 power p, this belongs to L, and its length 0 power p, 1 power p, its length is greater than equal to p. Will it pump? Will it pump? This string, will it pump? This string will not pump. This string will not pump. This string will not pump. If this string is not pumping, so can I say this string is not pumping? Whatever p you take, this string will not pump. See, whatever p you take, this string will not pump. So I can say this string we can use to prove that L is non-regular. Yes or no? So this string is useful to prove L non-regular. L is non-regular. Okay, very simple. This is useful because whatever p you take, this string will say I will not pump. Whatever p you take, you can take any value of p. This p can be 10, this p can be 100, p can be 1000. This p you can take any value. This string 0 power p, 1 power p, this string will say I will not pump. So this string will you can use this string to prove that L is non-regular. Okay, very simple. So this string is definitely your answer. I can say you got one answer. This answer you got. Okay, now what about the next string? What about the next string? Is there any doubt in this? Why this string will not pump? Is there any doubt? This we have already seen. If you remember in the previous lecture, this example we have already seen. We have already seen this. If you remember, this example we have already seen in part 2. Okay, you can check it out. Okay, so this string will not pump. Now, what about this one? 0, 0 power p, 1, 1 power p. Yes, this is a candidate string. This string is also a candidate string. Will it pump or not? Will it pump or not? The answer is this also will not pump. Will it pump? This will also not pump. Okay, you can the same logic for these two. Okay, you can use the same logic for these two. For these two, you can use the same logic. Okay, so this string will also not pump. So can I say this string option D you can use? So remember, so useful. So this string is useful to prove L is non-regular. That language L is non-regular. So this string is definitely useful to prove non-regular. Why? Tell me why. Because if you take this string, this is your string 0, 0 power p, 1, 1 power p. This is the string. So it's like 0, 0, 0, 0, 0, 0, and so on 0, 0. Then after that you have 1, 1, 1, 1, 1, 1, and so on 1, 1. This is your entire string. You tell me in which area you will find the y. In which area you will find y? You will find y in the first p symbols. Okay, somewhere's first p symbols. Let's assume these are the first p symbols. Let's assume these are the first p symbols. Now you tell me, in these first p symbols, you will find y. If you find y in these first p symbols, then tell me, if you repeat them 0 number of times, like whatever y you take, here I am saying that whatever y you take, see, whatever in this area, whatever y you take, whatever y, for example, you take this y, you take this y, you take this equal to y, whatever y you take this equal to y, whatever y you take, if you repeat 0 times, if we do this, if we repeat 0 times, what will happen? If you do this, repeat 0 number of times, then number of 0 will be less than number of 1. Number of zeros, that will be less than number of 1. Yes or no? Very simple. So number of 0, that will become less than number of 1, and that does not belong to L. So definitely I can say this string is not pumping. This string, that is not pumping. So whatever y you take, if you repeat it, this y, if you repeat 0 times, okay, then the resulting string will not belong to L. The resulting string will have less number of zeros than ones. Number of 0 will be less than number of ones. So this resulting string will not belong to L. Okay, so this, I can say this string will also help you. So I can say these are the answers. What about this one? This is not the answer. Okay, next, what about this one? 0 power p minus 1, 1 power p minus 1. What I can say about this one? 0 power p minus 1, 1 power p minus 1. So this is your 0 power p minus 1, 1 power p minus 1. Okay, this is your string. In this string, you tell me in which area you will find y. In which area you will find y? In which area? Remember, you will find y in the first these symbols, in the first p symbol. In the first, these are the first p symbols. Okay, these are the initial first p symbols. Okay, in these first p symbols, you will find y. Okay, so tell me which y will work. Which y will work? So I can say this y will definitely work. See, this 0, 1, this y works. This y will definitely work. You can repeat it any number of times. This y will work. You can repeat this y any number of times. Okay. So I can say this string will actually pump. Yes or no? I can say this string pumps. Okay, this string. What you can say, this string actually pumps. So this string pumps. So this is useless for us. If this string is pumping, so this is useless to prove non-regularity, to prove that L is non-regular. Okay, so very simple. So finally, your answer is what? Your final answer. So tell me, what is the final answer for this question? If this question comes in your GATE exam, then I can say these are the final answers. Okay, answer will be option C, D. These are your answers. Okay, so which string you can choose for your proof? Which string you can choose for your proof? So these strings you can choose for your proof. Okay, is this point clear? Please tell me. Let me know. Okay, so this is a nice question. You can check it out. Very simple. Now, is there anyone who got this answer? I gave you this question as a homework in the part 2. Is there anyone who got this answer? Did you comment on the part 2 on YouTube channel? Please do that. Okay, please do that. It will tell me that you are understanding the concept. Okay, so you can comment that you got this answer C comma D. Okay, so that will tell me that you are understanding the concept. Okay, let's move on. Now let's see this question. In this question, we want to find minimum pumping length. These are regular languages or not? These are regular languages or not? Yes, these are the regular languages. These are the regular expressions. You can notice these are the regular expressions. So these are the regular languages. Okay, you can create DFA also. You can create NFA also. The question is asking, give the minimum pumping length for these languages. So let's start with this one. The first one, 011 whole star. 011 whole star. This is your language. This is your regular expression for the language. Now you tell me, what will be the minimum pumping length? So first of all, you understand the language. Your language has 011, then 011, then 011, and so on. This is your 011, and so on. So this is your language. Okay, 011, then 011, next you have 011, something like this. So this is your language. Okay, also you have empty string also. Yes, you have empty string also. You have in this language you have empty string also. Now you tell me which p equal to which value will work. Which value of p will work? Can you directly tell me, just by looking at the language, can you directly tell me which p will work? Which p will work? See, definitely p less than equal to 2 will not work. Yes or no? P less than equal to 2, this will definitely not work. Okay, you can check it out. This will definitely not work. Whatever you do, this p, I can say p less than equal to 2, this will definitely not work. Why? What will happen? Tell me what will happen. P less than equal to 2, because for example this string will violate. Okay, you can take this string. So if you take, for example, even if you take p equal to 2, okay, let's assume you take p equal to 2. P equal to 2. So if you take p equal to 2, this is your string, this is your string. In this area you will find y. You will find your y in this area. Okay, in this area you will find y. So tell me how many y's are possible? Like, what are the possibilities for y? In this area you will find y. Now you can notice, if y equal to 0, then I repeat 0 number of times, what I will get? For example, if I take this equal to y and I repeat 0 number of times, which string I will get? Tell me. If I take this as y, I take this as y, I repeat it 0 number of times, the resulting string will be this. This does not belong to L. If I take y equal to 1, and I repeat this 0 number of times, what I will get? This is what I take. I take this equal to y. I repeat it 0 number of times. I will get 0, 1. That also does not belong to L. If I take this equal to y, means y equal to 0, 1. Now if I repeat this 0 number of times, then the resulting string will be 1, and that also does not belong to L. So whatever y you take, yes or no? So I can say whatever y you take, you can take whatever y you take. If you repeat that 0 number of times, then the result will not belong to L. The result is not going to belong to L. Okay, so you can notice p equal to 2 will not work. If p equal to 2 is not working, can p equal to 1 work? Tell me. If p equal to 2 is not working, I told you this point. If you remember, I told you this point, that for L, for any language L, whatever language you take, for any language L, if p works, then greater than equal to p will also work. Then greater than equal to p also work. Okay, that will also work. And similarly I can say, if p does not work, okay, or I can say, for example, if n does not work, okay, whatever value, for example, if t doesn't work, then less than equal to t will also not work. Yes or no? If t does not work, then less than equal to t also does not work. Okay, so very simple. This we have already seen, if you remember. So very simple point. So if t is not working, then less than equal to t will also not work. Okay, and similarly, if p is working, then greater than equal to p will also work. This we have seen in the last class. Okay, now you tell me, what about p equal to 3? Will it work? What about p equal to 3? Will it work? If I take p equal to 3, will it work? Yes, this will work. This will work, because, tell me, let's see the general solution directly. Let me tell you the general solution directly. See, whatever candidate string you take, First of all, what are the candidate strings? You tell me what are the candidate strings, means which strings matter to us, which strings we care about. We only care about these strings 011, 011, 011, and so on. These strings we care about. We care about these strings. Okay, now you tell me. So let's directly take the general solution. 011, at least 011 is there. Then there can be 011, then there can be 011, and so on 011. So this is your general case. I am directly taking the general case. Okay. Now you tell me. You tell me now. In which area you will find y? You will find y in this area. Yes or no? In this area you will find y. In this area you will find y. So tell me which y will work. In this area you will find y. So which y will work? Yes. This entire y you can take. This entire, this is what you can take as y. This y works. Okay, this y will work. You can repeat it any number of times. The resulting string will belong to L. Correct? Yes or no? Okay, you can repeat this 011. If you can repeat this any number of times, you can repeat this, and the resulting string will definitely belong to L. Okay, this will also work for this also. For example, if I take this string 011, if I take this candidate string, okay, let me take this candidate string, and if I repeat this 0 times, what will be the result? If I repeat this 0 times, then the result will be empty string, and that belongs to L. That belongs to L. Yes or no? So I can say for every candidate string, this first 011 will definitely work. Can I say? For every candidate string, the first 011 will definitely work as y. Okay, this first 011, this will definitely work as y. So this is your general solution. So for all candidate strings, I can say that they will pump. Every candidate string will pump. So I can say p equal to 3 is working. So for this language, remember, p equal to 3 works. Okay, so tell me, what will be the pumping length? If the question asks you pumping length, what your answer will be? Pumping length will be greater than equal to 3, any number of greater than equal to 3. And what will be minimum pumping length? If the question is asking minimum pumping length, then that will be 3. So this is your answer. And can I say, because this p equal to 3 is working, so can I say that this language satisfies pumping lemma? This language satisfies pumping lemma. The pumping lemma test, the exam of pumping lemma, this language has satisfied. Okay, this language passes the exam of pumping lemma. So very simple. Now you tell me the next language. The next language, let's take this before we will take this later, but let's take this 0, 0, 1 whole star 1. So tell me about this one, the second one, 0, 0, 1 whole star 1. First of all, you understand the language. Before solving the question, you at least understand the language. This is your language 0, 1. Then you have 0, 1, 0 like this. Okay. Then what you have? Then you have 0, 1, 0, 1, 0, 1. Okay. So something like this. Yes or no? Okay. Like this, you have the strings. Your strings are, these are the strings in the language. Okay. You can check it out. So these are the strings. For example, 0, 1, then you can have 0, 1, 0, 1, 0, 1. Okay, and so on. So these are the strings in your language. Okay, now you tell me. Remember, in this language, what is the minimum length string? In this language, what is the minimum length string? What is the minimum length string? What is the minimum length string? That is your 0, 1. Yes or no? Minimum length string has minimum length string, that is 0, 1. Okay, this has length 2. This has length 2. So tell me, the minimum length string has length 2. So can I say p equal to 2 cannot work? Yes or no? Minimum length in this language, minimum length string is this. This is the minimum length string. This has length 2. This has length 2. So I can say p less than equal to 2 cannot work. Okay, that you can directly say. You don't have to check. This we have already seen in the last class. In the part 2, we have already seen. Agree with me? This I already told you, if you remember. This was the note. In the last class, I told you that if this is your, let's assume you have a regular language. Let's assume that you have a regular language L. In this regular language L, let's assume these are the strings W1, W2, and so on. Now, assume in this I can say, if minimum length string, or I can say shortest length of shortest string, what is that? if length of shortest string, is m, then tell me what pumping length can never work. If length of shortest string is m, then I can say which pumping length can never work. Then P cannot be less than equal to m. Yes or no? Then P is never less than equal to m. Then P cannot be less than equal to m. Or I can say that P will definitely be greater than equal to m. Okay. So I can simply say that P cannot be less than equal to m. Means I can say P equal to m cannot work, can never work. Okay. This we have already seen in the last class. Now let's move on. So in this, from where you will start? Tell me, from where you will start checking? You will start checking from P equal to 3. Will it work? P equal to 3. Will it work? Will it work if I take P equal to 3? Is this going to work if I take P equal to 3? First of all, for P equal to 3, what are my candidate strings? You give me my candidate strings. Okay, give me what are the candidate strings. Which strings I care about if I take P equal to 3? Then I care about these strings. This string, then this string. Okay. Then you can notice 0, 1, 0, 1, 0, 1, 1, this string and so on. These are the candidate strings. Now you tell me, I have P equal to 3. Okay. So now let's start with this string. For example, let's start with this candidate string. Okay. Let me check this candidate string 0, 0, 1, 1. Can it pump? First of all, this is your string. Let's take this string. In which area you will find Y? Your Y must be in this area. Okay. In this area, you must find Y. In this area. Okay. First 3 symbols, you should find Y. So tell me which Y will work. Is there any Y which will work? Take this Y. Take this Y. Take this equal to Y. This Y will work. What is the problem? This Y will work. This Y will work. Why? You can easily notice 0, 0, 1, 1. Okay. In this area, you need Y. Your Y must be in this area. Your Y must be. These are the first 3 symbols. These are the first P. P is equal to 3. These are the first 3 symbols. Okay. In these, you find Y. I am telling you that this Y will work. Take this equal to Y. If you take this equal to Y, what is your X? If I take this equal to Y, what is your X? X is 0. What is your Z? Z is 1. Okay. Now you tell me, it's like X, Y power N, Z. What string I will get? If I repeat this Y any number of times, basically any number of times, I am repeating this Y any number of times. I am repeating this star means any number of times. This star means any number of times, correct? Yes or no? Any number of times, greater than or equal to 0, any number of times. So can you notice your X is 0. Okay. This Y is 0, 1. You can repeat it any number of times. And your Z is 1. Yes, definitely these strings belong to L. These strings definitely belong to L. Yes or no? So you can notice the resulting string will belong to L. The resulting string will belong to L. So this is the point. Okay, so I am saying that this string will also pump. This string will also pump. Whatever string you take. See, whatever string you take, that will pump. For example, even this string will also pump. If you take 0, 0, 1, 0, 1, 1. If you take this string also, that will also pump. Okay, this string you take. In this string also, in this area, you will find Y. Okay, in this area, you will find Y. Now, I can say that this Y will again work. This Y will again work. Okay, so whatever string you take, I can say, okay, this is the general solution. Let me give you the general solution. So what will be the general solution? The general solution will be that you take whatever string you want. I'm just saying that 0, 1, and there are some 0, 1, 0, 1, 0, 1. Okay, some 0, 1 and so on. Now, there are some 0, 1, 0, 1 and so on. Okay, now you can notice whatever string you take, I'm saying that within the first 3 symbols, this 0, 1 will definitely work. Okay, this Y will definitely work. Okay, is this point clear? This is your general solution. So I can say P equal to 3 works. Yes or no? So for this language, I can say P equal to 3 works. Did anyone get this answer? Is there anyone who got this answer? Did you get this answer? I gave you this question as a homework. Did you get this answer? Your analysis, did you do the correct analysis? Your analysis was correct, can I say? Did you do the correct analysis? Yes, answer will be P equal to 3, but did you do the correct analysis? Okay, very good. So I can say P equal to 3 works. So remember, for this language, what is the pumping length? What is the pumping length? Pumping length will be any number greater than equal to 3. Okay, that will be any number. Pumping length will be any number greater than equal to 3. And what will be the minimum pumping length? That will be 3. Okay, so this is the idea. I hope all these points are clear. Now let's move on. Let's take this question. This question is remaining now. So let's start with this one. 0011. Now your language is this. 0011. Is your language finite? Can I say your language is finite? Yes, only one string is there. Your language is finite. You tell me one thing. This is your language. And did you notice one thing? In pumping lemma, one observation did you make? Okay, one observation. I want you to make one observation. Okay, so just make this observation. Let me call it observation. This is not a complicated observation. Just make this observation. Let's assume L is regular. Okay, assume L is regular. Assume L is, so let's assume L is regular. In L, okay, so I can say let L be regular. L is a regular language. Okay, now you notice one thing. In this L, if P works, in this L, I am saying if P works. Okay, if P works, let's assume P is working. I am telling you that P is working. You don't have to check. You don't have to check. I am telling you that P is working. Okay, is this point clear? I am telling you P is working. Okay, so I am telling you it is given that P is working. It is given. It is given that P is working. Okay, now tell me one thing. In this language, P is working. If there exists in this language, if there exists a W in this language, who is candidate string? If there exists, okay, if there is some, remember, so if there is some string in this L whose length is greater than equal to P, then tell me one thing, will it pump? Will it pump? Will W pump? Then W will pump. Yes or no? Then definitely W will pump. Because I'm telling you L is regular, and I'm telling you it is given that P is working. So if you take this type of string from this language, then this W will definitely pump. And if this W will pump, then will this W create infinite number of strings? This W is pumping. This W is pumping. Remember, this W will pump. Okay, there will be some Y. There exists some non-empty Y. Okay, there is some non-empty Y. Because W is pumping. So W has some non-empty section Y. Such that, can I say W, can I say X, Y power N, this will belong to L? Yes or no? This will belong to L. But if you do this, then your language will be infinite or not? If you do this, then your language will become infinite. Okay, because this N you can put 0, 1, 2, 3, 10, 100, 1 trillion, 1 million. Okay, so if you do this, this creates infinite number of strings. This creates infinite number of strings it will create. This creates infinite number of strings. Infinite number of strings it will create. Okay, so your language will become infinite. Yes or no? Your language will become infinite. So I can say, so language L becomes infinite. So definitely in such situation L becomes infinite. Okay, your language will become infinite. So you tell me one thing. Okay, this is the conclusion. Let me tell you. This observation, did you understand? Please tell me. This observation, did you understand? See, if L is regular and it is given that P is working. It is already given to you that P is working. Now, if there is some candidate string, if there is some string whose length is greater than or equal to P, then that string will pump. That string will definitely pump. Okay. Now, if this string, which is in the language, this string is in the language, and this string has length greater than or equal to P, so this string will definitely pump. And because this string is pumping, so it will create infinite number of string. Because this string is pumping, this W is pumping, so W will create infinite number of strings. W will create infinite number of strings by pumping. By pumping. Yes or no? By pumping these many times. Is this point clear? This W will create infinite number of strings by pumping any number of times. Correct? This is what I'm saying. This W, this will create infinite number of strings by pumping any number of times. So your language will become infinite. Your language, that will become infinite. So actually what I want to say, I just want to say that if you have a regular language, if L is regular, okay, I just want to say that if L is regular, okay, and there exists a pumping, if L is regular, comma, pumping length is P. Okay, if L is regular and pumping length is P, then please focus on this word. If there exists a candidate string, then L will be infinite. Can I say? If there exists a candidate string, then L will be infinite. Please tell me, is this point clear? Did you understand? See, very simple point that L is regular and pumping length is P. Okay. If L is regular and pumping length is P, if there exists a candidate string, then L will be infinite. This point, did you understand this point? Please tell me. Is there anyone who can say that, yes, I understood this point? Anyone has any doubt in this point? Anyone? Please tell me. Anyone has any doubt in this point? Simple point. See, if there exists a candidate string, then that will pump also. Okay, just think about it. If there is candidate string, your language is regular, pumping length is P. Now, you tell me one thing. If there is candidate string, okay, if there is a string which is candidate string, means it belongs to the language and its length is greater than or equal to P. So if there is a candidate string, then that will pump also. Yes or no? Because pumping length is P. It is given to you. Pumping length is P. So if you have candidate string, there is at least one candidate string if you have in the language. Okay, if there is at least one candidate string, then that will pump also. Yes or no? That string will pump also. And by pumping, that string will create infinite number of strings in the language. Yes or no? Every candidate string will pump. And by pumping, they will create infinite number of strings they will create in the language. So this is what I'm saying, that if your language is regular, so definitely it will satisfy pumping lemma. Every regular language will satisfy pumping lemma. So every candidate string will pump. Now, if there is at least one candidate string, then that string will create, by pumping, that string will create infinite number of strings. So your language will become infinite. Yes or no? Did you understand this? Please tell me. So you tell me one thing. If your language is finite, then there cannot be any candidate string, right? Yes or no? Please tell me. This is the point that I want to convey, that if language is finite, if language is already finite, then there cannot be candidate string. Because if candidate string is there, then that will pump, and that will pump any number of times, that will pump, and that will create infinite number of strings. So final conclusion is, if your language is already finite, then there cannot be a candidate string. Do you agree? If your language is finite, then there cannot be a candidate string, because remember this point, candidate strings will pump and they will create infinite number of strings. Your language will become infinite. Okay, so please tell me, did you understand this simple point? Did you understand? If you understood, that is very good. See, if you understood, then it is very good. If you did not understand, let me just tell you this simple thing you just need to remember. If you understood, very good. Okay, this point that I told you, if you understood, then it is good. If you did not understand, don't worry. Okay, if not understood, this point that I told you, if you not understood, then don't worry about it. Okay, then don't worry. Okay, then don't worry. Either you can watch this, basically this explanation, either you can rewatch. Okay, rewatch this explanation and maybe you can work it out. Take copy pen and do it. Or you can just forget about it. Just don't worry about it. Just take this conclusion. Okay, I'm giving you a conclusion. Just remember this conclusion. Okay, just remember this conclusion. If you have a finite language, L, okay, for example, if you have, let me give you, like, if you have this finite language 0 0 1 1 0 1 1, okay, 1 0 1 1 0, okay, now you tell me this is a finite language, so this is regular. Every finite language is regular, yes or no? Every finite language is regular. So this is a finite language. Every finite language is regular. Okay, every finite language is regular. Every regular language will satisfy pumping lemma. Every regular language will satisfy pumping lemma. Okay, that will satisfy pumping lemma. Okay, now you tell me, every regular language means this language will also satisfy pumping lemma. This language that is given to you, this language will also satisfy pumping lemma. So what will be the pumping length? Which pumping length will work? Which pumping length will work? So which pumping length will work? So that which pumping length will work? Let me tell you simple point. This is the largest string, can I say, in this L? This is the largest string in L. This is the largest string in the language L. What is the length of this string? What is the length of this string? This string has length 9. This string has the length 9. Okay, so can your pumping length be less than equal to 9? In this language, can you take pumping length less than equal to 9? A simple question. You will understand. Just don't worry. Just give me, let me explain. Let me explain. See, this is your language. Okay, some strings are there. Some strings like 0 0 1 1, then 0 1 1, then 1 0 1, and there is another string that is 1 0 0 1, then you have 0 1 1 0 1. Now in this language, you just tell me, this will satisfy pumping lemma, right? Yes or no? Because this is a regular language. This is a regular language, so it will satisfy pumping lemma. So it will definitely satisfy pumping lemma. And if it will satisfy pumping lemma, then there is a pumping length. Then there is a pumping length. We also have a pumping length. Then we have a pumping length. Okay, now you tell me, can this pumping length work? Pumping length is also there. Okay, now you tell me, can this pumping length work? For example, if I take pumping length equal to 8, then if I take this pumping length equal to 8, but remember this longest string, this is the longest string. Remember, this is the longest string. This is the longest string in L, whose length, this is the longest string whose length is equal to 9. If I take p equal to 8, will it become candidate string? Please tell me. If I take p equal to 8, if I take p equal to 8, will this become candidate string? This string, let's call it W. Will this become candidate string? So remember this point. If you take pumping length, equal to this, then this W, this will become candidate string. Okay, yes or no? If you take pumping length equal to 8, then this will become candidate string. This will become candidate string. And because now this candidate string will pump, so will it create infinite number of strings or not? This string will pump because this is a candidate string. Pumping lemma is satisfied. So if you take pumping length equal to 8, then this string will pump, and it will create infinite number of strings. It will create infinite number of strings. So your language will become infinite, but your language is finite. So where is the problem? Where is the problem? Your language is already finite. Okay, if you take p equal to 8, if you take p equal to 8, then this string will become candidate string. Now this string will pump and it will create infinite number of strings. So, but your language is already finite. So where is the problem? The problem is that this pumping length is wrong. Yes or no? The problem is that this pumping length is wrong. This pumping length is wrong. Yes or no? Okay, so the problem is this pumping length is wrong. Is this point clear? This pumping length is wrong. Because of this pumping length, this string is becoming candidate string. Okay, and if this string becomes candidate string, then this will create infinite number of strings by pumping, and your language will become infinite. So in simple words, I can say that this p equal to 8, this is a wrong candidate string. In simple words, I can say, from this I can say p equal to 8 is wrong. So tell me which value of p will work? Let me tell you. Just take p equal to 10. If you take p equal to 10, there will be no candidate string at all. Yes or no? If you take, just assume, if you take p equal to 10, then there are no candidate strings. Now there are no candidate strings. If there are no candidate strings, if there are no candidate strings, then no pumping will happen. Yes or no? No pumping will happen. And because no pumping is happening, so L will not become infinite. Okay, L will not become infinite. L will not become infinite. Yes or no? L will not become infinite. Please tell me, did you understand this? This is the final point. See, this is the longest string. What you do? This is the longest string. If this longest string has length, I can say this is the longest. This is the longest string. And its length is 9. You take p equal to 10. You take p equal to 10. Now there is no candidate strings now. Now we don't have any candidate strings. If there is no candidate strings, then there is no violation. There is no pumping. There is no violation. I can simply say no candidate strings means no violation. There is no candidate string, so there is no violation. So there is no pumping. So L will not become infinite. Simply I can say that it's like in Hindi. There is a metaphor in Hindi. Have you heard? Na rahega बांस ना बजेगी बांसुरी. So if you take p equal to 10, ना रहेगी candidate string, okay, ना होगी कोई problem. Okay, so something like this. You can remember like that, okay, if you want. So whatever I told you in the last 15 minutes, in the last 15 or 20 minutes, whatever I told you, this is the conclusion. Okay, I'm giving you the conclusion now. In the last 15 or 20 minutes, whatever I told you, I'm giving you the conclusion. The conclusion is simple. If you have a finite language, then what will be the pumping length? What will be the minimum pumping length? For finite language L, what will be the minimum pumping length? Tell me. For this finite language L, minimum pumping length will be minimum pumping length will be m plus 1. What is m here? Minimum pumping length will be m plus 1. What is m here? That is the length of longest string of L. Length of longest string of L. Okay, is this point clear? Because simple. See, this is a simple point. You have a finite language. That L. This is your finite language W1, W2, W3, and so on, Wn. Okay, let's assume this is the longest string. Assume this is the longest string. Okay, assume this string is longest string. So this string is longest string. Now you tell me, if this string is longest string and I take p equal to length of this string plus 1, then what will be the candidate strings to check? If I take this p, then what are the candidate strings to check? What are the candidate strings to check? None. There is no candidate string to check. There is no candidate string, because remember W3, this is the its length. Okay, W3 length plus 1. If I take this, candidate strings will be none. ना रहेगा बांस, ना बजेगी बांसुरी, something like that. If there is no candidate string, then there is nothing. Okay, there is, it will not pump. Hi all, am I audible? Is it lagging? Please tell me. Is it fine now? Now is it fine? Let me know. Let me know. See, as soon as you feel there is a lagging, as soon as you feel that there is a lagging, please let me know. Okay. Now is it clear? Please tell me. My voice, audio, video, lagging, is everything clear now? Let me know. Okay. So I'm just saying that if you take P equal to length of longest string plus 1, if you take P equal to this, then there will be no candidate string. You know, na rahega baans, na bajegi bansuri. So there is no candidate string, so there is no problem. So I can say this P, this will work. Okay, this will work, and I can simply say this is your minimum pumping length. This is your minimum pumping length. Is this point clear? So for this language, what will be the minimum pumping length? Minimum pumping length. That means minimum pumping length. So what is the minimum pumping length? That will be 5. 5 is the minimum pumping length. The answer will be, or I can say the answer will be 4 plus 1. What is 4 here? That is the length of longest string of L. Length of longest string of L. Okay, because this language is finite. So this is your formula. So for finite languages, you never have to worry. You never have to worry. For finite languages, you never have to worry. Okay, so this is a simple point that for finite languages, all you have to do, for finite languages, all you have to do, for finite language L, just make sure there is no candidate string. Okay, so for finite language L, just take P equal to length of longest string plus 1. Length of longest string plus 1. Okay, this is a length of longest string. Length of longest string in L. Okay, plus 1. So remember this P will definitely work. Okay, this P will definitely work, because what we have done, if you take this P, then there will be no candidate strings. Yes or no? If you are taking this P, then there are no candidate strings. So this is the smart move. This is a smart move, that basically you are just making sure that there is no candidate string at all. You are making sure there is no violation at all. We have no problem. We have no violation. Okay, so you can just take this P equal to M plus 1, that will work. And remember, this is also the minimum pumping length. So very simple. This is your final answer. Now let's move on now. So this point we have seen. Okay, you can read this statement. This point, assume L satisfies pumping lemma. See, let me just tell you. Assume L satisfies pumping lemma. If there exists at least one candidate string, then that candidate string will create infinite number of strings by pumping. Yes or no? Please tell me, read this statement and tell me, did you understand this statement? If L satisfies pumping lemma, L already satisfies pumping lemma, and there exists at least one candidate string, then that candidate string will pump. That candidate string will pump. Okay, because L is satisfying pumping lemma. L satisfies pumping lemma. Now, every candidate string will pump. Yes or no? If language L satisfies pumping lemma, then every candidate string will pump. So in your language, if you have at least one candidate string, then that will pump, and that will create infinite number of strings. So that is the reason. That is the reason that for finite languages, answer will be this. So this is the final point. If language is finite, then minimum pumping length of L will be M plus 1, where M is the length of longest string, where M is the length of longest string in W. Okay, is this point clear? Where m is the length of longest string in L. Okay, now let's move on now. So very easily you can see for this question the answer minimum pumping length, that will be 5. Okay, for the remaining, for this what was the answer? Minimum pumping length was 3, and for this what was the answer? Minimum pumping length was 3. Okay, so these are the answers. Okay, now let's see this one, the question number 4. This question number 4, what this is saying? The question number 4 is saying that if S is non-empty regular language with pumping length P, with pumping length P, then prove that S contains some string with length strictly less than P. How will you prove it? How will you prove it? Did you understand the question? The question is saying if S is a regular language, non-empty regular language, whose pumping length is P, then S definitely contains some string whose length is strictly less than P. How will you prove it? See, you can prove this like this, because if you have L is regular language, okay, the question I can say, let's call it question number 4. So in this question number 4, S is a regular language. The question is saying that S is a regular language. Now you tell me one thing. S is a regular language. Okay, just see, the proof is actually very simple. If S is non-empty, the question is already saying that S is non-empty. You tell me if S is non-empty, can I say there is a minimum length string? S is a regular language. It can be finite, infinite, but the point is, whatever language you take, S is a regular language. This can be finite or this can be infinite. This language can be finite or language can be infinite. But the point is, in this S, there exists a minimum length string. There exists a minimum length string. Can I say? There exists a minimum length string, because whatever language you take, just take any language. Whatever language you take, finite or finite or infinite, whatever language you take, you will always have some smallest string, yes or no? At least one smallest string will always be there. At least one smallest string will always be there. You tell me one more thing. Can I say that at least one longest string will always be there? Whatever L you take, whatever non-empty, this question, please tell me the answer for this question. Whatever non-empty L you take, can I say there exists shortest string? Can I say there exists shortest string? And can I say there exists a longest string? Which statement is correct? Which statement is correct? Tell me. Which statement is correct? Whatever L you take, finite or whatever non-empty L, it can be finite or it can be infinite. Whatever L you take, what can you say? Can I say there exists a shortest string? Yes, this will definitely happen. Can I say there exists a longest string? No. Can I say there exists a longest string? No. Why? For example, take this L equal to sigma star. What is the longest string in this? Tell me what is the longest string in this. Tell me what is the longest string. Tell me. And what is the shortest string? Tell me what is the shortest string. See, the shortest string is empty string. Tell me the longest string. What is the longest string? What is the longest string? There is no longest string. There is no longest string. Is there any string of infinite length? Is there any string of infinite length? No, I told you every string has finite length. This I told you repeatedly many times in the basic lectures. Every string always has finite length. Let me write it very big, because some students are making mistake. Every string always has finite length. Is this point clear? Every string always has finite length. So you tell me, in this language, is there any longest string? There is no longest string, but there is shortest string. If a language has longest string, then what can I say about this language? If a language L has longest string, has a longest string, has a longest string. Tell me, if a language has a longest string, what can you say about L? Then L will be, definitely finite. Then L will be definitely finite. Yes or no? Then L will definitely be finite. Then L will be finite. Okay. So this is the simple point that if L is finite, then there is, I can simply say, if L is infinite, then there is no longest string. L infinite implies there is no longest string. There is no longest string. Yes or no? If L is infinite, that implies there is no longest string. In L, we have no longest string. So simple point. Okay. So these points, these small points, they have nothing to do with pumping lemma. Yes or no? These statements, these small statements, these are basic statements. These are basic questions. Okay. So let's come to our question. Now, our question number 4. Let's come to this question number 4. So you tell me one thing. You tell me one thing. S is non-empty regular language. Okay. So this S, this is non-empty. This language is non-empty. So there is at least one string in this language S. There is at least one string. Now this S, this can be finite or infinite. But the point is, whatever language you take, there will be a minimum length string. Yes or no? There exists a shortest string. Correct? There exists a shortest string. Okay. Now you tell me, there exists a shortest string. Let's assume that string is W. Okay. Now you tell me. So for this S, what will be the pumping length? What will be the minimum pumping length? Tell me. What will be the pumping length? We have already seen in the last class. In this S, in this language S, minimum length string is this. This is the minimum length string. Then what will be the pumping length? That will be greater than or equal to its length plus 1. Yes or no? Agree or not? Agree or not? Correct? Or I can simply say that that will definitely be greater than equal to length of W. That will be definitely greater than equal to length of W. This we have already seen in the last class. And this is what this question is asking. Did you notice? This is what this question is asking. That if pumping length is P, for a non-empty regular language, then there is some string with length less than P, strictly less than P. Please tell me, did you understand? This question number 4 is basically asking this. Yes or no? Is this clear? You have non-empty regular language. You have non-empty regular language S. You have this non-empty regular language S. Now, in this, you have some strings, W1, W2, and so on. Now, let's assume this string. Let's assume this string is shortest string. Let's assume this string is shortest. Now, I told you in the last class, what I told you? I told you that for this, the pumping length, for this language, the pumping length will definitely be greater than length of this. The pumping length will definitely be greater than length of this. Okay. So if pumping length is P, then there exists a string whose length is strictly less than P. Yes or no? If pumping length is P, then there exists a string whose length is strictly less than P. This is what this question is asking. So we have done this question. Did you understand this question? So this is actually a nice question, let me tell you. This question is actually a nice question. Why this is a nice question? Because see, it's like this. This thing many students know. Yes or no? Many students can answer this question. Many students can answer this question. But the same question we are asking in indirect way. Indirectly, we are asking this question. Correct? Okay, so this you can notice. This is the indirect way of asking this question. Indirect way of asking this question. So tell me, so far, is everything clear? I think this class has become a little bit heavy. Some students are not getting few points. So let's take 1 minute. let's take small break, some pause. Let's take a pause. Let's take a pause. Okay. What I am going to tell you now, the conclusion I will tell you. Okay. Just remember that conclusion. Okay. Just remember that conclusion, and you can forget about the entire class that has happened today. In the entire class, whatever we have seen, okay, so you can forget about that and just remember these two conclusions. You remember that I am going to tell you now. Just remember these conclusions. The proof I told you, I tried to tell you the proof. Okay. But if you did not understand the proof, then don't worry about it. Please do not worry about it. I promise you, no one will ask you. Okay. The proof that we have seen, only one proof is important. That is proof of pumping lemma that we will see today. Only that proof is important. That is really important proof that we will see today. But in this class, okay, before now, before this moment, whatever we have seen, you can forget about that. If you understood, very good. If you understood 50%, very good. If you understood 80%, then also very good. And if you understood only 10%, then also very good. I'm just giving you the conclusion. Just remember these conclusions. Agree with me? Are you with me? I am giving you two conclusions. Just remember these conclusions. These are very simple conclusions. You can remember these conclusions. Okay. So let's see. What are the conclusions? Let's see. So let me tell you the conclusions so far. In today's class, whatever we have seen, let me conclude. Let me conclude. So far, whatever we have seen, so far, only two things matter to us. Only two things. The first thing is, what is the minimum pumping length of finite language? Yes or no? Minimum pumping length of finite language means for finite language, what will happen? For finite language L, what will happen? For finite language L. So for finite language L, what will happen? You have this direct formula. You don't even have to check. For finite language, you don't even have to check. There is a direct formula. Minimum pumping length is equal to minimum pumping length. That is equal to m plus 1. Where what is m? What is m here? This m, this is the length of longest string. Longest string in L. Okay, clear? Is this clear? So minimum pumping length, that is equal to m plus 1, where m is length of longest string in L. This simple result, can you remember? Can you remember this simple result? Very simple result. Okay, very simple. So just remember this result. Just remember it. Now let's see the second result. What is the second result that we have seen? The second result is, if you have language L, okay, if W is shortest string in L, if W is the shortest string in regular language L, then tell me what will happen. Then tell me what will happen. If W is shortest string in regular language L, then what can I say? I can say pumping length will be definitely, this pumping length, this will definitely be greater than length of W. Okay. This pumping length will definitely be greater than equal to, greater than length of W. Okay. This same statement we can write indirectly. This same statement in an indirect way. Okay. Indirect way of 2. What is the indirect way of 2? Means this same statement we can write in an indirect way. And what is that? That is that if L is non-empty regular language, if L is non-empty regular, okay, and pumping length is P, then tell me what you can say about L, and pumping length is P, then what will happen? See, this same statement you can write in an indirect way. In this statement, we are saying that if W is shortest string, then pumping length that will be strictly greater than length of W. So can I say length of W is strictly less than P? Length of W is strictly less than P. So yes, so the same thing I am saying that if L is non-empty regular language, if L is a non-empty regular language and pumping length is P, then there exists some string, then there is some string with length less than P. Then L has some string, at least one string, L has some string W with length strictly less than P. That's it. So these things, only these things we have seen today so far. Now can you say that you understood these three statements? Did you understand these three statements? Did you understand? Please tell me. Okay, so simple. You tell me one more thing. If pumping length is greater than equal to length of W, so what about minimum pumping length? That will also be greater than equal to W. Yes or no? Minimum pumping length will also be greater than equal to length of W. Simple point. The minimum pumping length that will also be strictly greater than length of W. Okay, so these things, so very simple. I hope all these points are clear. So that's it. Okay, so whatever was heavy in this lecture, whatever you did not understand, now just forget about it and just understand these statements. Now are you feeling good? Only these statements matter. Forget about what you did not understand. In today's class so far, whatever you did not understand, forget about it. Forget about it. Don't try to understand. I am telling you. Okay, do not worry about it. 0%. 0% you have to worry about it. So forget about what you did not understand. Just remember these conclusions. That's it. Now the important point we need to discuss, that is proof of pumping lemma. Okay. Now what we need to discuss, now just focus. Now we need to discuss the proof of pumping lemma. This is what we need to discuss. But before that, let's see the formal definition of pumping lemma. So far, we have seen the definition of pumping lemma, we have seen, but we can write that as a formal statement. Okay, so very simple. So tell me what pumping lemma says. Let's write pumping lemma in a formal way. Let's write. So what pumping lemma says? Okay, let's write it. What pumping lemma says? So pumping lemma, what it says? It says that if L is regular, what will happen? Tell me. If L is regular, then what pumping lemma says? Tell me. If L is regular, then what will happen? Then there exists a pumping length. Okay. If L is regular, then there is some positive integer. Yes or no? If L is a regular language, then there is some positive integer. There is some positive integer P. There is some positive integer P. Correct? Very simple. Okay. If L is regular, then there is some positive integer P, such that what will happen? Tell me. Such that what will happen? Such that every such string, such that every W, which type of W? These W which belong to L and whose length is greater than equal to P, such that every W pumps. Yes or no? Every W pumps. Very simple. These are the candidate strings. These are your candidate strings. So every candidate string pumps. So this is the same thing we can write like this. So there is some positive number P such that for every W, belonging to L, okay, such that for every W, or I can say such that for every W, such W belongs to L and length of W is greater than equal to P. So for every such W, what will happen? Every W which will satisfy this property. Hi all, is there any lagging issue? I think my internet is not stable today. I think the internet is not stable right now. Okay, so let's see the this formal definition, and then maybe we can continue this proof maybe tomorrow or okay. So let's finish this formal definition. Okay, let me just tell you the formal definition. Then maybe we can continue the proof. The proof we can see maybe tomorrow we can see. Okay. So let's see. Pumping lemma says if L is regular, then what will happen? If L is regular, then there is some positive integer P such that for every W, every this type of W, such that for every W, okay, what will happen? Tell me. What will happen? Every such W means every candidate string W. What I can do with that? I can write that as XYZ. Yes or no? Correct. I can divide this. This W I can divide as XYZ. This W I can divide as XYZ. Such that then again what will happen? Such that for every W I can divide this W as XYZ such that what will happen? What are the conditions? Okay, such that these are the conditions that first of all Y is non-empty. Y cannot be empty. Yes or no? I can say this is the first thing, Y cannot be empty. The second thing, tell me this XY, it will belong to which area? This XY, it belong to which area? Within the first P symbols. So this XY, it will belong to within the first P symbols. And the third point, that you can repeat this Y any number of times, the result will belong to L. The result will belong to L. So this is your pumping lemma statement. This is the formal statement of pumping lemma. Did you understand? Please tell me. So simple, see, this is the simple point. You have a regular language. Let me write a regular language. If there is a regular language, then what will happen? Then there exists a magical number. Then there exists a magical number. This is a magical number. Okay. So I can say there exists a magical number such that again what will happen? Again what will happen? For every W which belongs to L and length is greater than equal to P, for every such W, what will happen? For every such W, which this happens, for every such W, W can be broken as XYZ. Okay, every such W can be written as XYZ. Can be written as XYZ. Okay. What are the properties of this XYZ? What are the properties of this XYZ? The length of Y, that is definitely greater than equal to 1. Okay, Y is non-empty. Y is non-empty. So length of Y, that is greater than equal to 1. And this XY, it will be within the first P symbols. Agree? This XY, this will be within the first P symbols. So this XY, this will be within the first P symbols. And also, I can repeat this Y any number of times. I can repeat this Y any number of times. The result will belong to L. This is your pumping lemma. This is the pumping lemma. Understood? See this. This is taken from Stanford University. For any regular language, just read this one time. Okay, read this one time. For any regular language L, there exists a positive natural number. Correct? For any regular language L, there exists a positive natural number. This is basically your P. Yes or no? This is your pumping length P. This is the pumping length. Such that for any W whose length is greater than equal to P, for any W in the language whose length is greater than equal to P, you can write this W as XYZ. You can write this W as XYZ. This W you can break as XYZ, such that these three properties will be satisfied. These three properties will be satisfied. This XY will be within the first P symbols. Yes or no? This XY, this is your W, XYZ. I can say this XY, this will be within the first P symbols. Within first P symbols. Within first P symbols. Within first P symbols. So that we are writing like this. Y is non-empty. And you can repeat this Y any number of times. The result will belong to L. the result will belong to L. This is your pumping lemma formal statement. Understood? This is the formal statement of pumping lemma. Please tell me, understood? Simple. So this is your formal statement. Okay, you can read this. The same statement from Washington University. So this slide is taken from Stanford. Let me tell you. This slide I have taken from Stanford. You can read this. I've already told you. The next slide. This slide is taken from Washington University. You can read this. The same. This is taken from Washington. Okay. You can read. All these things we have seen. Now we need to study the proof of pumping lemma. But today my internet is not working. So this we will study tomorrow. Okay. Because the internet connection is not stable today. So we will study this proof tomorrow. Today, whatever we have seen, did you understand? See, the internet is not stable. So I think if we continue, then in between it will glitch. Okay, there will be some lagging, there will be some breaking of voice. Okay, there will be some issues. Okay, so that is the reason I am thinking that we can continue this tomorrow. Okay, tomorrow we can continue. Today, whatever we have seen, did you understand? Please tell me. First, we have seen 2 examples. I gave you 2 homework questions. Those homework questions we have seen. You understood those homework questions, can I say? The first homework question, did you understand? First and second, those homework questions, did you understand? And then this conclusion, did you, or this conclusion you can remember? Okay, so in this lecture, we have seen homework question. Those homework questions you understood, very good. Next, we have seen some conclusions. 2 conclusions we have seen. 2 conclusions we have seen. One for finite languages. For finite language, what will happen? That I told you. You can remember it. Don't worry about the logic. Okay, don't worry about it. In today's class, whatever you understood, that you take. Whatever you did not understand, don't worry about it. Okay, I'm telling you, honestly, I'm telling you, if you did not understand the logic, some logic, if you did not understand, forget about it. Okay, so then we have seen the formal definition of pumping lemma. These 3 things we have seen. Okay, so please tell me now. Actually, the purpose of this lecture, the purpose was to see the proof, but due to weak internet connection, we will continue the proof tomorrow. Okay, I will finish the proof tomorrow, and tomorrow I promise you this pumping lemma will finish. Actually, today I could have finished it, but don't worry, tomorrow we will complete this pumping lemma. Okay, is that clear? Tomorrow will be the last class of pumping lemma, and then there will be a quiz only for pumping lemma. Okay, there will be one quiz only for pumping lemma, only for pumping lemma. Okay, anyone has any doubt, you can ask. Satyam is asking some doubt. Please tell me. Yes, Satyam, any doubt? Satyam is asking, for any language, if there are no candidate string to violate pumping lemma, then by default, is that language considered to satisfy pumping lemma? Satyam, actually, for finite languages, you are saying there is no violating string. Then yes, it will satisfy pumping lemma. If you have a language, any language you take, if you have a language, and for that language you have some p such that there is no violating string, then yes, the language will satisfy pumping lemma. Are you getting my point? See what I'm saying? This is what I'm saying, that if you have language p, if you have language L, okay, let me just tell. If you have language L, and for this language L, okay, for this language L, if for some p there is no violating string, okay, if for some p, okay, if for some p, remember, if for some p there is no violating string, then what I can say? there is no violating string, there is no violating candidate string, then what I can say? There is no violating candidate string. Then else satisfies pumping lemma. 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 And the pumping length will be P. And the pumping length will be P. And the pumping length will be P. Is this clear, Satyam? For language L, if for some P there is no violating string, if for some P there is no violating string, then L will satisfy pumping lemma and pumping length will be P. Okay. So this is the idea. Now, one more thing. If for language L, for every P, there exists a violating string. There is some violating string. Then what you can say, tell me? There is some violating candidate string. Then what you can say, tell me? There is some violating candidate string. There is some violating candidate string for every P. Then pumping lemma is not satisfied. Okay. Then L non-regular. Then L non-regular. Okay. Because then L fails pumping lemma. L fails pumping lemma. So L non-regular. So this language L will be non-regular. Okay. Is this point clear? Let me know. So this is the idea. Any other doubt? Satyam, is your doubt clear? Please tell me. Is there any other doubt? Rohit Raj is asking, sir, for the first question, that is language consisting of a string equal number of 1 and 0, does 0 power p plus n, 1 power p plus n for any natural number, it violates? Yes, that is correct. That is correct. Rohit, that's correct. So, see, you are asking this question. Our language was this: number of 0 equal to number of ones. Number of 0 equal to number of ones. This was our language. Now, for this language, for every p, what you can take? For every p, okay, for any p, like for any p, you can take any p. Your choice. You can take any p. For any p, what you can do? You can take this string 0 power p. Okay, 0 power p. Now there can be more also. For example, 0 power p plus n, 1 power p plus n. Okay, as long as n is greater than or equal to 0. You can take this string. This string will also violate. This string will also violate. Means this string will also not pump. This string will also not pump. This string will also not pump. Okay, so L non-regular. So L fails pumping lemma. Is this clear, Rohit? Rohirat? Any other doubt? Any other doubt is pending? Please tell me. Shivani is asking, according to definition, we are considering the string greater than pumping length. So what about the smallest string? No, Shivani, the proof we will see tomorrow. In the proof, you will understand that basically the candidate strings, we only care about those strings which belong to the language and whose length is greater than or equal to the pumping length. Okay, so that you will understand in the proof. Tomorrow you will understand in the proof. I think your doubt will be clear once you see the proof. Okay, so don't worry about it. The proof is very interesting. The proof is easy and interesting. And we will also see some questions which are based on the proof. Means if you don't know the proof, then you cannot solve those questions. So this type of questions also we will see. Okay. Any other doubt, anyone? Please tell me. Any other doubt, anyone? Let me know. Is there any pumping lemma for non-regular languages? No. For non-regular languages, there is no pumping lemma. There is pumping lemma for regular languages. There is pumping lemma for context-free languages. But So far, there is no pumping lemma for other languages. Okay, maybe you can do PhD in theory of computation. Maybe you can create your own pumping lemma for some other languages. Okay, so Shivam, these things, they are, I can say, they are a matter of research. If you do research in theory of computation, if you do research in the automata theory, then you can find out new things. Okay, pumping lemma of context free languages is not in the syllabus. Don't worry about it. Okay, only one pumping lemma matters. In the syllabus also you can check. In the syllabus you can check. In the GATE syllabus you can check. Pumping lemma of regular languages, only that is in the syllabus. No other pumping lemma is in the syllabus. Pumping lemma of context free language is not in the syllabus. You can check the syllabus also. The GATE syllabus you can check. Someone is asking, is there any non-regular language which will satisfy pumping lemma? Yes, I will give you one example tomorrow. Okay, I will give you one example of non-regular language which will satisfy pumping lemma. I will give you that example tomorrow. Don't worry about it. Okay, one example I will give you. Any other doubt? Any other doubt? Okay, thank you everyone. See you tomorrow. Tomorrow will be the last class of pumping lemma. Okay.